You know when you hit run on your code, what's actually happening in that split second? Your words, your logic, they're about to go on this really fascinating journey. And in this explainer, we're going to follow that journey from your screen all the way down to the machine's core language.
So let me ask you this. What language does your computer really speak? I mean, at its very core, deep down in the silicon. It's a pretty fundamental question, and, well, the answer might actually surprise you.
Because here's the thing, it's not Python or C++ or JavaScript. To really get what's going on, we're going to follow a single line of code on its journey, all the way from your screen to the processor. Let's trace its path.
Okay, so our story begins where all programming does, right? With an idea, an expression, written in a language that's designed for us, for humans, to read and write.
So let's meet our main character for this little journey, this simple line of C code. Now, to us, it's pretty clear. We're taking an element from an array, we're multiplying it by 4, and then adding 2. But to the computer? Right now, this is just a sequence of symbols. It doesn't mean anything, at least not yet.
So how does a computer even start to make sense of this? Well, this is where a program called a compiler steps in. You can think of it like a translator, whose only job is to turn our human-readable code into something the machine can actually execute.
The very first thing the compiler does is break down the grammar of our code, kind of like how you diagram a sentence in English class. It builds this structure called a parse tree. And if you look closely, you can see how every little piece of our original code, even the brackets, has a specific place here. It's a very, very literal map of the code's structure.
But then, things get a little cleaner. The compiler simplifies that parse tree into what's called an abstract syntax tree, or an AST. See how the brackets are gone? That's because the tree now understands the idea of accessing an array element, not just the symbols for it. It's captured the core meaning. And this step is absolutely crucial, because this clean structure is what allows for all the powerful analysis that comes next.
You know, just because the grammar is right doesn't mean the code actually makes sense. So the next step is called semantic analysis. Here, the compiler starts asking questions like, okay, is A really an array? Is index a number? It adds this layer of context to make sure the logic holds up. And actually, this is where the compiler catches a whole bunch of bugs for you, long before your program even tries to run.
Okay, now we've reached a really interesting point. The compiler translates our code into this sort of universal machine-like language called intermediate code. It's basically a series of simple instructions where each one has, at most, 3 parts, like result equals operand 1 plus operand 2. The cool thing is, this language isn't tied to any specific type of computer, which makes it a perfect middle step. All right, our code has been parsed, it's been analyzed, and it's been translated into this universal format. Now it's time for the final leg of the journey, turning it into a language for a specific machine.
This destination language is called the target language, or target code. And it's exactly what it sounds like, the final, fundamental set of raw instructions that a particular CPU, like the one in your laptop or your phone, can understand and execute directly. This is it. This is the computer's true native tongue.
And here we are. This is our line of code, translated into assembly language, which is really just a human-readable version of the final machine code. Instructions like move, mul, and add. These are direct commands for the processor. Our code has finally reached its destination.
But, you know, just arriving isn't the end of the story. The first translation is often correct, but it's not always the most efficient. And the compiler has one more trick up its sleeve, a final polish. So take a look at this. On the left is the first version of our machine code. On the right is the optimized version. See how MULR04 became SHLR02? That's a bitwise shift, which is a much faster way for the computer to multiply by a power of 2. The compiler made our code smarter and more efficient, taking it from 5 instructions all the way down to 3. This is really where the art of compilation comes in.
So we followed our single line of code on this incredible journey. And it's a fascinating process, right? But why does understanding it actually matter for you as a programmer or as a student? Well, for starters, when you understand what the compiler is doing under the hood, you start to get a feel for why some code is just plain faster than other code. You can start to write programs more intentionally. And those really confusing error messages from the compiler, they start to make a whole lot more sense. Ultimately, it just gives you this deeper appreciation for the elegant, logical process happening just beneath the surface every time you code. So the next time you write a line of code, maybe you'll pause for just a second.
and think about its journey. Because every app, every game, and every website you use is built on this silent, foundational language, constantly being translated just out of sight.